Okay. I hope I'm audible and my screen is also visible to you. Um, so let's start our seventh tutorial session. Tutorial 7, Advanced Linear Algebra. Mhm. 03. And today is 8th March 0803. Okay. So um, let's start some problems. So let's recall some facts before giving you solutions. Invariant subspace. Invariant subspace. Let V be a vector space over a field F and T from V to V be a linear operator on G. Okay. Then a subspace W of V is said to be invariant subspace if T of W is subset of W. So if we take elements from W and map it, then it will map to W again. So then T is said to be, then W is said to be invariant subspace corresponding to the um, linear operator T. Okay. So now uh, now let's do one question. So problem number 1. Let T be a linear operator from the column vectors of 3 order R3 cross R31 to be a linear operator defined by T of x is equals to Ax, where A is the matrix 1 1 minus 1 is the matrix 1 1 minus 1 2 0 minus 1 2 2 minus 2. Okay. So then and let S1 is equals to all the vector of the form 2x, y, x whole transpose, that is column vector, such that x and y are coming from R, and S2 is equals to all the vector x, y and 2x whole to transpose such that x and y are coming from R. S3 is equals to minus 2x 0 x transformed such that x is coming from R, and S4 that is equals to x 0 minus 2x transform such that x coming from R are all subspaces of R3 cross 1. Then question is which of these subspaces are invariant subspace corresponding to the linear operator T. So options are giving like this. S1 is T invariant but not S2. Option B, S1 is T invariant but not S1. Option C, S3 is T invariant but not S4. And option D, it is said that S4 is T invariant but not S3. So which of these are correct? So let's try to find. So Tx is given by the matrix, this A matrix. Okay. So then let's write T of a vector. Let's take a vector 2x y 2x. This is equals to the matrix 1 1 minus 1 2 0 minus 1 2 2 minus 2, this one with multiplication 2x y 2x, then this will be equals to 2x plus y minus 2x. Okay. And the second one will be I think okay, x y, this is x, this is x, this is x, so this is x for considering x, considering s1 here. So this will be x and this will be 4x minus x, and next will be 4x plus 2y minus 2x. Okay. So this is nothing but x plus y. This is 3x and this is 2x plus 2y. So this can be written as x plus y 3x x plus y 2. So note that elements in so therefore this is this element, this note that elements in S1, which is elements of collection of this type of elements, that is the first term is the double of the third term. So here it is not the case. Here first term is not double of the third term, but instead of third term is double of the first term. So that's why this is not belongs to S1. Okay. So therefore S1 is T invariant, that is itself false. First one. Okay. Now we'll check whether S2, S3 and S4, these three vector space are T invariant or not. So recall that this S2 is equals to S2 is equals to X, Y, TX transpose such that X and Y belongs to R. So let's take T and vector X, Y and 2X. Okay, so then what we'll get, this is equals to the matrix 1 1 minus 1 2 0 minus 1 2 0 minus 2, this one with the vector x y 2x, then this is equals to x plus y minus 2x 2x minus 2x 2x minus 4x. So this will be equals to y minus x 0 and the minus 2x. Okay, so overall the elements in S2 is given looking like that the third term is the double of the first term. Okay, but here it is not the case. Okay, I think this is, I have written little 2x minus 4x. I think I have written little, this is 2. This is 2. So this will be 2x plus 2y minus 4x. So therefore this will be x y minus x 2 of y minus x. So here the first term is here note that the first term is actually double of the third term is the double of the first term. So therefore this element is again in S2. Therefore S2 is invariant under T. But here S1 is not invariant under T. So okay, now we'll take the third one. What third one says that S3 is equals to, so therefore this option is correct. S1 is T invariant but not S2. I think I have written S2 is T invariant but not S1. S2 is T invariant but not S1. This option is correct. Okay, so we'll prove that S3 and S4 are also not T invariant. So what is S3 here? S3 here is actually minus 2x comma 0 comma x whole transpose such that x is coming from R, and so therefore let's write an element 2x 0x, this is equals to 1 1 minus 1 2 0 minus 1 2 2 minus 2, this one along with minus 2x 0x, this is equals to, it will be minus 2x minus x, minus 4x minus x minus 4x minus 2x. So this will be equals to minus 3x minus 5x minus 6x. So therefore, one can look at the middle term should be 0, but here it is not necessarily. So, so therefore, this is not in S3. So S3 is not a not a T invariant subspace, not a T invariant subspace of V. Similarly, so therefore third option is incorrect. S3 is a T invariant subspace, that is incorrect. So let's check S4 is T invariant or not. Where S4 is equals to given by this way, x comma 0 comma minus 2x whole transpose, such that x is coming from R. Then T of x0 minus 2x, this is equals to 1 1 minus 1 2 0 minus 1 2 2 minus 2, this one along with x0 minus 2x, this can be written. So therefore we will get x plus 2x, x plus 2x 2x plus 2x, this is 2x plus 4x, so this will be 3x 4x 6x. So here is also the second term will be the minus 2 times of the first term, but that is not the case, so therefore this is also not true. X plus 2x, I think I'm correct. Huh. So this is also not the case. So therefore, this is not belongs to S4. Therefore, S4 is not a T invariant subspace of V. Therefore, last option is also not correct. Okay. Now we'll do another problem that is also similar problem, but I will not do that. Okay. The next one is says that let problem. What it says, let W be a finite dimensional subspace of the inner product space. So you can consider it as vector space, because till now the no inner product space has been discussed in the course. V and E be the orthogonal projection of V on W, and if x is equals to the polynomial x cube plus 5x square plus 3x plus 2, let f of E is equals to A identity plus BE, then A and B can take which of the following values? Which of the following values? Option A can be taken as 9, B is equals to 2. Option B, A equals to 1, B equals to 8. Option C, A equals to 2 and B equals to 9. Option D, A equals to 8, B equals to 1. Okay. So let's see what will be the correct option. Recall that if V is a vector space, then a projection E from V to V is a linear operator such that satisfies the relation E square is equals to E. So if E is a linear operator, if it satisfies the relation E square equals to A, then it is called the projection. Okay, so therefore, as f is a f of E, then what I can say about f of E? F is given as a polynomial, so f of E will be E cube plus 5E square plus 3E plus 2 times identity. Therefore, E cube can be written first E square, then we can write it as again E is E, so this will be E plus 5E plus 3E plus 2, that 2 times identity, that means this is 2 times identity plus 9 of E. So therefore A can be take value A identity plus B, it is question. Okay, so A can take value 2 and B can take value 9. So therefore option C is the correct option. So therefore all other options are automatically false. Okay. Now I'll do another problem. Questions 4. Question some problem. What it says, this is an interesting problem. Suppose we are giving a linear operator. So before that, let's go to the what is called projection. Projection on a vector space. Let V be a vector space over a field F, and E from V to V be a projection. That is, E is a linear operator for which, that is, E is a linear operator for which it satisfies the relation E square equals to E. Then take R is equals to range of E, okay, and N is equals to null space of E, okay. Then first, then it is clear that then R is called R is range of the projection E, and N is the null space of the projection E. Then uh, R E is called projection on E along the subspace along N. Note that this R and N are all are subspace. So here A is called projection on E along N. Okay. Why in general call it this way? For as if I consider an element in R that is range of then there exists a element V beta in V such that alpha is equals to E beta, then E alpha is equals to E of E beta, then E square beta, but we know E is the orthogonal E is projection, therefore E square equals to E, therefore E beta, as E square is equals to E, so this is alpha. So what we are getting that for any alpha belongs to R, E alpha is equals to alpha. Okay, so that's why it is saying that E is the projection on the range space R and along with the null space N. Okay. So now suppose we are giving suppose some informations about the orthogonal projection it is given. So then if one wants to find orthogonal projection as a linear operator, then how one can find? Okay, so this type of problem we will discuss now. Problem. But it says let E be a projection operator which projects R2 onto the subspace spanned by the vector 1 minus 3 along the subspace spanned by minus 1 1. Then question is, then which of the following statement is your correct? Okay, so option A, EXY is equals to minus x plus y by 2 minus 3x plus y by 2. Option B, E of x and y is equals to minus x plus y by 2. Here it is minus means minus is outside, okay? Comma, minus x plus y by 2. Option C, EXY is equals to minus of x plus y by 2 minus of 3x minus y by 2. And option D, minus of x minus y, okay, this is also x minus y, by 2, this is also outside, then minus of x minus y by 2. So these are the options. So which of these following are correct? Okay, so here, so therefore what it is saying that E is an orthogonal projection. E is a projection for which range R is equals to the span of the, it is saying that it is projection on the subspace spanned by the vector 1 comma minus 3 along the vector that is null space. Is along the vector minus 1 comma 1. Along these vectors it is asked. So therefore the here it is asked what is the expression of E. Okay, so now, so therefore E of 1 comma minus 3, that must be 1 comma minus 3, but E of minus 1 comma 1, that must be 0 because that is in the null space. So now the standard order basis 1 0 that can be written, let's take it can be written in this form 1 comma minus 3 plus b minus 1 comma 1. Therefore this will be a minus b minus 3a plus b. So it will be getting a minus b is equals to 1 minus 3a plus b is equals to 0, and this will give the d is equals to 3a, and this will give a minus 3a is equals to 1, that will give a is equals to minus 1 by 2. Therefore one will get b is equals to minus 3 by 2. And similarly, if one wants to find 0 1 in terms of a 1 minus 3 plus b of minus 1 comma 1, that is equals to a minus b minus 3a plus b, then one will get a minus b is equals to 0 and minus 3a plus b is equals to 1. Therefore a equals to b, and this will give minus 2a equals to 1. This will give a equals to minus 1 by 2, and B is equals to, therefore as A equals to B, this will also be minus 1 by 2. Therefore, for any x and y belongs to R square, this x and y can be written as x 1 comma 0 plus y 0 comma 1, and and then E of x and y is equals to x E 1 comma 0 plus y E 0 comma 1. But E1 comma 0, here if you note that E1 comma 0 is equals to this way, where A is equals to this, therefore 1 comma 0 is equals to minus 1 by 2 1 comma minus 3 plus minus 3 by 2 minus 1 comma 1, and so this one is the one thing. This is one thing, and another is 0 comma 1, this is equals to minus 1 by 2 1 comma minus 3 plus minus 1 by 2 1 comma 1. So this is another. Okay, so these two are the things. So now what we are getting, so therefore E10 is equals to, that is minus 1 by 2 1 comma minus 3, and E01, that is equals to minus 1 by 2 1 comma minus 3, as this is getting 0 and this is getting 0. So therefore what we are getting here actually, Exy is equals to x into minus 1 comma 1 minus half into 1 comma 0 and plus y into 1 by 2 1 comma minus 3, that will give minus 1 by 2 x plus y, and minus 3 by 2, this is plus I think, minus plus x plus y. So this is the expression of E. So this is the correct option, then all other options will be false. Now for the next problem, we'll state a theorem. Okay, and after that we'll go to the that problem. So theorem says, let T be a linear operator on a finite dimensional vector space V over a field F. Let T is diagonalizable and C1 all the way Ck are all distinct eigenvalue, are the distinct eigenvalues of T, are the distinct characteristic values of T, then there exist linear operators E1, E2 all the way Ek on V, such that T is equals to C1 E1 all the way Ck Ek. Option 2, I equals to E1 all the way Ek. Option 3, Ei Ej is equals to 0, I not equals to j. And option 4, Ei square is equals to Ei, that is all Ei are projection. And option 5, the range of Ei characteristics or eigenspace of T associated with Ca. associated with Ci. Conversely, if there exists k distinct value 1 to C1, C2, Ck for and subspace E1, E2 and or linear operator E1, E2, Ek, which satisfy the condition 1 to this condition, this one, this one, this one, and this one, this four condition, then T is diagonalizable and C1, C2, Ck are the corresponding all possible distinct eigenvalues. All are the distinct eigenvalues, and in that case, uh, other will be satisfied. But the interesting fact what we are just want to say here is that suppose we have minimal polynomial and also okay T is defined by this way. Okay, so then also we will state another theorem. Linear operator on a finite dimensional vector space V is diagonalizable if and only its minimal polynomial is completely factorized into distinct linear factors. That is what it is saying is that the that is if C1 to Ck are all possible eigen values, all distinct eigenvalues of T, then T is diagonalizable obviously on a finite dimensional vector space if and only its minimal polynomial must be of the form Px is equals to x minus c1 x minus c2 all the way x minus ck. So therefore, here we are seeing that if T is a linear operator which is defined on a finite dimensional vector space V and T is diagonalizable and C1, C2, Ck are distinct characteristic values, then there exist linear operators E1, E2, Ek. They are actually the they are actually the projections on the eigenspaces of V, eigenspaces on V, and such that T will satisfy this condition and T will satisfy this condition and all other condition is there. So now question is how this EI one can say, okay, we know that this EI are orthogonal projections, but they are also linear operator and they are linear operator related to the linear operator T. So the question is how this linear operator EI is defined in terms of T. And here, uh, then this EI is equals to, this will be written as product of all I, which is all j, which is not equals to j not equals to I, j equals to 1 to k. So one will write j equals to 1 to k and j not equals to I. Then this will be x minus c1 all the way x minus ci minus 1 x minus ci plus 1 x minus ck divided by ck sorry ci minus c1 ci minus c2 all the way ci minus ci minus 1 ci minus ci plus 1 all the way ci minus ck. So this is the thing. So um, so this way one can write this. Okay. So therefore, for a linear operator, so therefore I will give discuss a problem on the basis of this. What problem is saying that let T be a linear operator. Let T be a linear operator finite dimensional vector space V over F with dimension of V is equals to n, given that given 1, 3 and 5 are distinct eigenvalues of T such that I is equals to E1 plus E2 plus E3 and T is equals to E1 plus 3 E2 plus 5 E3, then which of the following statement is or correct? Then which of the following statement is or are correct? First option, E1 is equals to minus 1 by 8, T minus 3 times identity, T minus 5 times identity. B E2 is equals to minus 1 by 4, T minus identity, T minus 5 times identity. And option C, E1 is equals to minus 1 by 3, T minus identity, T minus 5 times identity. And option D says E2 is equals to minus 1 by 3, T minus 3i, T minus 5i. So, on the basis of the above discussion, so on the basis of the above discussion, here it is asking for E1 and E2, not E3. So E1, so here we have, so okay, first starting with the some different way. So it is clear that the linear operator T is diagonalizable. I think this is not written here, but this is diagonalizable because T has all the property which is supposed to be satisfied by this theorem. T satisfying all these theorem, and conversely T will be linear but diagonalizable. So here clearly T is diagonalizable. First, by above discussion, E1 E1 will be minus, not minus, E1 will be x minus C2, that is the eigenvalues corresponding to 1, that is 3 x minus 5 by 1 minus 3 1 minus 5, that is equals to, this is minus 2 minus 4 1 by 8 x minus 3, oh sorry, this is t minus 3. I'm just typing. Okay, I think I have written correctly. This at t. This ei is equals to pit, where pix is equals to this. Therefore, here it will be t minus lambda times identity, 3 times identity, 3 times identity into t minus 5 times identity. So therefore, this will be t minus 3 times identity and t minus 5 times identity, right? But this is not the case. Okay, so therefore E1 is not satisfying this one. So what is E2? E2 will be t minus identity and t minus 5 times identity by 3 minus 1 and to 3 minus 5. So therefore this is 3 minus 5 minus 2, 3 minus 1 minus 1 by 4. 1 by 4 t minus identity t minus 5 times identity. Okay. So therefore this option is correct. E1 is not false. So E2 can't be correct. So E1 is not satisfying this option. So option B is the only correct option. Okay. So now question. Now we'll do another question. What it says, let V and W are two finite dimensional vector space over a field over R, and let V and W are two finite dimensional vector space over a field R, and let T1 from V to V and T2 from W to W be linear operator, linear transformation is same thing, transformation whose minimal polynomial whose minimal polynomial whose minimal polynomials are given by f1x, which is equals to x cube plus 3x square plus x plus 3, and f2x, that is corresponding x4 minus 2x square minus 3, and let this f1 and f2 are the correspondingly linear minimal polynomial of the linear operator t1 and t2. Okay, let t be the linear operator from v direct sum w to the vector space v direct sum w, be the linear transformation, be the linear transformation given by t vw is equals to tv tw. Okay, we know t and v already. Okay, sorry, t not t1 tv, sorry, t1v t2w. Okay, for all v and w in the direction, v and w coming from v direction w. Okay, okay, let f be the minimal polynomial, let f be the minimal polynomial of t, then which of the following is correct? Which of the following statement is or are correct? So option A, degree of fx is equals to 7. Option B, degree of fx is equals to 5. Option C, nullity of t is equals to 1. And option D, nullity of t is equals to 0. So here one can look at that v and w both are separate vector space. Okay, and v direct sum w here, this is a two finite dimensional vector space over the field R. Okay, here v direct sum w already is a vector space of uh, separate vector space basically. So therefore, for any linear operator, I mean, how one can write here, just want to say the matrix representation of V and W will be the block diagonal. Okay, let beta 1 and beta 2 are two orthonormal bases of V and W respectively. Then the matrix representation of T will be then matrix representation of T will be this way. T with respect to the basis beta 1 union beta 2. That union may not be, this is direct sum it is taking. So there must be sum defined. So in that way, this will be, one can write T beta 1, that is 0, 0, T beta 2. And recall that recall that minimal polynomial of a linear operator on a finite dimensional vector space V is the smallest degree monic polynomial. Monic polynomial means the polynomial with the leading non-zero, I mean coefficient of the highest degree term is 1. Polynomial monic polynomial P such that P equals to 0. Therefore, f1 of tb1, that will be 0, and f2 of tb2, that is 0, and f1 and f2 are the smallest polynomial for which these two are happening. So therefore, if f of t wants to be 0, then f must be in this form, f1 dot f2. So therefore, f of x is equals to product of these two polynomials, that is x3 plus 2x 3x square plus x plus 3 into x to the power 4 minus 2x square minus 3. Okay, so therefore degree of f of x is equals to 7. Option A is correct, and simultaneously option B is false. Okay, note that eigenvalues of t b eigenvalues of t are union of t are union of eigenvalues of t1 and t2, but as t1 and as t1 and t2 are t1 and t2 does not have eigenvalue 0, 0. Why t1 and t2 does not have eigenvalue 0? Because 0 is not root of 0 is not root of 0 is not root of f1. 0 is neither root of f1 or nor f2. 0 is root of the polynomial f1 nor f2, because minimal polynomial should contains all the factor corresponding to the eigenvalue, but here as f1 and f2 does not have 0 as the root, therefore, so the f1 and f2 does not contain the factor x, so therefore f1 0 is not the eigenvalue of t1, neither eigenvalue of t2 nor eigenvalue of t1, so therefore 0 is not eigenvalue of t. So if 0 is not an eigenvalue of t, therefore null space of t is equals to 0. That implies nullity is equals to 0. That implies option D is correct, as well as option C is false. So nullity of t is, this is correct, this is false, this is false, this is correct. Okay. So now we will do another problem. Let E be a projection of a vector space V, and let T be a linear operator on V. Then which of the following statement is or are correct? Option A, null space of E is invariant under T. Option B, a range space of E is invariant under T. Option C, if range space of E invariant under T, then Et equals to T. And option D, if ETE is equals to T, then the range space of E is invariant under T. T. These are the four options we will looking for. So therefore we will look at this, but before this we'll just discuss one theorem, and we'll prove that small theorem. I think that is proved by in class, I think. So okay, so then I'll only state the theorem. theorem says that okay, no need to prove the theorem. I will just discuss this theorem. So here it is let that E be the projection on vector space V and let T be the linear operator on V. Then um, which of the following statement is or are correct? Okay, so first option, null space of E is invariant under T. That is true or false. That is not necessarily true. Why? Let's take E be the projection of vector space. Okay, let's take T is the linear operator from R2 to R2, which is given by T of uh, x and y is equals to 0 goes to x, like this way. This is a linear operator, no doubt about it. Is a linear operator. So therefore, E is the projection. If I write E is the projection, okay. If I write E is the projection, let and E from R2 to R2, which is given by E of x and y is equals to 0 y. This is the projection. Okay. Then null space of E is equals to x comma 0 such that x is coming from R. Okay. Therefore, but but for any element x comma 0 in null space of E, one can look at the T of x comma 0 that is equals to 0 comma x. That is not contained in null space of E. Okay, so therefore null space of E is not invariant under T. So therefore first option is false. Then second is that range space of E is invariant under T. That is also not false. So one can take E from R square to R square given by E of x and y. So option A is false. This one says that option A is false. Exy is equals to x comma 0. Then range of E that is equals to all the element of this form. X is belongs to R, right? This is the range space. Okay, but range of E is not invariant under T because we have seen few seconds ago that this space, this set is not invariant under T. Therefore, option B is also false. So here is the natural questions when a projection PE is orthogonal, when a projection E is when the range space or null space. Okay. When so therefore question is when the range or null space of a projection is invariant under T, linear operator T. So the answer will give here. So the answer is when they commutes. And so in particularly we'll give interestingly we'll prove another reason. So let E be the projection on the E. Okay, so we'll prove B and C are correct. So range of E is invariant under T. If range of E is invariant under T, if range of E is invariant under T, then for any alpha belongs to the vector space V, T of E alpha that is in the range that is equals to E beta for some beta is in V, right? That is in the range of, because range of, because it, because range of, for example, if I take an element alpha belongs to V, E alpha is in range, then T, then E range will be invariant if T of E alpha is again in range. That means T of E alpha is image of some element under E, and if I assume that that element is beta, so we are assuming like this way, T is equals to B. So therefore, E T alpha is equals to E square beta, that is equals to E beta, as it is projections, and this is equals to again T E alpha, and this is true for all alpha belongs to, this is true for all alpha belongs to the vector space V. Therefore, ETE is equals to TE. Therefore, option C is correct. If the range space is invariant under T, then ET equals to TE. Now we will show that the last one. If ET equals to TE, then range space of E is invariant under T. This is also true. We will show that. Let ETE is equals to TE. ETE is equals to T. This is very interesting, and this will be useful uh, for inner product space as well, whenever one will consider E as the orthogonal projection instead of just arbitrary projections. So here E is the projection. So if E is projection, range space will be invariant under T if and only Et equals to T. We have seen that if range space is invariant under T, then Et equals to T. Now we'll show that Et equals to T, then range space is invariant. Then range space of E is equals to some vector E alpha, alpha be coming from V. Then we have to show that T of E alpha is something. But T of E alpha is equals to E T of alpha. That is again contained in the range of E. That's all. Therefore, range of E is invariant under T. So therefore, one can state that from here, let V be a vector space over a field F, T be a linear operator on V, and E be a projection on a subspace, projection on V, projection on a subspace of V. Then the range of E is invariant under T if and only ETE is equals to TE. Okay, so this is what we are getting. Now we will prove another problem. We will discuss another problem. Where it says let V be a finite dimensional vector space over F, and dimension of V is equals to n. Let W1, W2 and W3 be any proper subspace of V such that W1, plus W2 plus W3 is equals to V, then which of the following is correct? Then which following is correct? First one, V is equals to W1 direct sum W2 direct sum W3. Second one, 2 dimension of V is greater than is equals to dimension of W1 dimension of W2 dimension of W3 minus dimension of W1 intersection W2 intersection W3. Option C, dimension of V is equals to dimension of W1 dimension of W2 dimension of W3 minus dimension of W1 intersection W2 intersection W3. And the last option B, V is equals to W1 direct sum W2 plus W3 if W1 intersection W2 is 0 and W2 intersection W3 is 0. So before saying this, what is direction that I will write? Let V be a vector space, W1, W2 all the way Wk are subspaces of V. They are non-trivial subspaces. That means they are not zero. Okay, the subspaces of V. Okay, then this is just sum. Okay, this is sum means any element of the form will be alpha 1 all the way alpha k such that alpha I belongs to Wi is a subspace of V. Now W1, W2, Wk are said to be independent. Said to be independent if all the way alpha k equals to 0, where alpha I are coming from Wi, implies that alpha I equals to 0 for all I equals to 1 to all the way k. Okay. So, or this is if and only this is equivalent to some fact that this is equivalent to fact that Wi intersection W1 plus all the way Wi minus 1 plus Wi plus 1 plus Wk, this one is empty, zero set contains for all I equals to 1 to k. So these two factors are independent, these two factors same. These two factors said that W and W are said to be independent if it satisfies this condition, imply if and only. So this is the if and only. This is the if and only. If alpha 1 plus alpha 2 plus alpha equals to 0, alpha I belongs to Wi implies alpha equals to 0. That happens if and only if Wi intersection W1 sum Wi minus 1 plus W I plus 1 and all the Wi plus k is equals to this is 0. These two fact is called independent. Okay, and then in and in that situation, in that situation, that is when W1, that is when this set W1 all the way Wk are independent, then the sum W1 plus W2 all the way Wk is called direct sum and written as if and in that case in that case dimension of W1 direct sum W2 all the way direct sum Wk is equals to dimension of W1 plus dimension of Wk. This is the case. So let's get back to the problem. So it is said that if W1, W2, W3 are any subspaces such that W1 union W1 plus W2 plus W3 is equals to V, then whether option A, that is V, is the direct sum of W1 plus W2 plus W3 or not. So here, if I want to prove that option A is correct, what we need to show is that this W1, W2, W3 are independent. But that is not necessary. For an arbitrary 3 subspace for which the sum is vector space V, for that case, it is not necessary that W1, W2, W3 will be what is called they are independent. Okay. For example, let's take V is the vector space R3 and W1 is actually span of the vector 1 comma 0 comma 0 and 0 comma 1 comma 0, and W2 is actually span of 0 comma 1 comma 0 0 comma 0 comma 1, and W3 is span of 1 comma 0 comma 0 0 comma 0 comma 1. So then clearly V is equals to W1 plus W2 plus W3, but this W1, W2, W3 are not linearly independent. Therefore, not independent, nothing. Therefore, but V is not equals to W1 direct sum, W2 direct sum, W3. Here actually direct sum is not possible. So therefore, option A is false. Option A is false. Now, here it is saying the dimension of V equals to dimension of W1, W2, W3 minus dimension of W1 intersection W2 intersection W3. Okay. So, here is also with the same example, above, with the same example of above, W1, W2, W3, dimension of W1 with same 2, that is dimension of W2, that is dimension of W3, but W1 intersection W2 intersection W3, that is contains only 0. So dimension of W1 intersection W2 intersection W3, that is equals to 0. So therefore dimension of V, that is actually 3, that is not equals to dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 intersection W3, which is equals to 6. So therefore option B is also false. Okay. So option C is also false, not B. This is option C. Option B I'm not getting right now. So I'll go to option C. So now we will prove that option D is false. What D is saying that V is equals to W1 direct sum W2 plus W3 if W1 intersection W2 is 0 and W2 intersection W3 is 0. So we will prove this. So we will prove that We'll construct W1, W2, W3 for which the V is the sum, but this is not happening. Okay, so let's take option D. Actually, we want to prove option D. Let's take V is equals to R4 and W1 is equals to 1 comma 0 comma 0. This is 0 comma 1 comma 0. As the this is as the W1 span, and W1 and W2 should be disjoint. W2 is equals to span of 0 comma 0 comma 1 comma 0, and W2 and W3 should be disjoint. W3 is equals to span of 0 comma 0 comma 1 comma 0 and 1 comma 0 comma 0. Okay, so therefore what we are getting here actually, note that here W1 and W2 are in 0 and W2 W3 is also 0. So note that W1 intersection W2 is 0. There is no common vector. And W2 intersection W3, that is again no, this is 0 comma 1. Okay. W2 intersection W3, that is again 0 because there is no common vector. And as well as W1 plus W2 plus W3, that contains all the vector, that is equals to the vector space V. Okay. But W2 plus W3, that will be span of 0 comma 0 comma 1 comma 0, 0 comma 0 comma 0 comma 1, 1 comma 0 comma 0. So therefore W1 intersection W2 sum W3, this is not 0. Therefore V can't be written W1 direct sum W2 plus W3. This way can be written because if we want to write two subspace as direct sum, we first need is that their sum is the vector space and that their intersection is disjoint. I mean their intersection is contains only zero set trivial. But here W1 contains this vector 0 1 comma 1 comma 0 0, but W2 plus W3, that is also contains 1 comma 0 0. Therefore, this one is non-empty and contains non-zero. So therefore, this is the case. So option D is false. So option D is false. So therefore, only option C B is remaining. But let's try to prove this one. So the option B says that two dimension of V. Option B, that dimension of V, 2 of dimension V, that is greater than is equals to dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 intersection W3. This is happening or not? Okay. First of all, here we'll look at that dimension of W1 that is strictly less than V, dimension of W2 that is strictly less than V, dimension of W3 that is also strictly less than V, and dimension of W1 intersection W2 intersection W3 that is also strictly less than V. So minus dimension is greater than equals to um, how one can prove dimension of W1. How one can prove the dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1. intersection W2 intersection W3 that is less than equal to dimension of V. Okay, it is known that this is the, so this is correct. I hope this is correct. Let's check. Okay, one thing, 1 minute. This is 2, this is 1, this is 2. So, 2, 1, 2, 5, W1. Okay, we know dimension of W1, W2, W3. This is equals to dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 minus dimension of W2 intersection W3 minus dimension of W1 intersection W3 plus dimension of W1 intersection W2 intersection W3. Now, now dimension of W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3, this one minus dimension of W1 intersection W2 intersection W3, that must be less than equals to dimension of V. That is for sure, because W1 intersection W2 intersection W2 intersection W3 intersection W, this is the case. Okay, okay, okay. Okay, just 1 minute. I'll prove it. So note that W1 intersection W2 plus W2 intersection W3 plus W1 intersection W3. This is subspace of the vector space V. Therefore, dimension of this W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3 minus dimension of W1 intersection W2 intersection W3 minus dimension of, okay, basically what I want to prove here is that this is the formula of three element direct sum of three element, sum of the three element. So dimension of V is greater than is equals to dimension of W1 intersection W2 plus W2 intersection W3 plus W1 intersection W3, that is equals to dimension of W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3. Okay, so minus dimension of W1 intersection W2, that is intersection with W2 W3, that is intersection same, minus dimension of W2 intersection W3 intersection W1 W2, that is again W1 W2 W3 minus dimension of W1 intersection W2 intersection W1 W2 W3. So this is the case, and plus dimension of W1 all the intersection, and that is again W1 intersection W2 W3, and therefore what we are getting here actually, that is equals to dimension of W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3 minus 2 dimension of W1 intersection W2 uh, intersection W3, and this is less than equals to dimension of V. Therefore, let's mark it 1. So from 1, what we are getting is that dimension of V is equals to dimension of W1 plus dimension of W1 plus W2 plus W3. This is equals to uh, dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3 plus dimension of W1 intersection W2 intersection W3. Therefore, note that this particular full thing, this full this full thing is less than equals to this one. So minus of this greater than equals to hmm, so I can write it is like this way also. Okay, got it. Okay, so from here, what we can say here is that dimension of W1 intersection W2 plus dimension of W2 intersection W3 plus dimension of W1 intersection W3 minus 2 dimension of W1 intersection W3. This is less than or equals to dimension of V. So here we have adjusted this. So therefore, minus of this is greater than is equals to minus of this. That is what we want to use. Therefore, here we will use this one. Minus of this is greater than or equals to minus of this particular term is as it is. Keep it as it is. This red one is the this one, and minus dimension of W1 intersection W2 intersection W3. Therefore, what we are getting is that dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 intersection W3, that is less than is equals to 2 times dimension of V. This proof. So therefore, option B is correct. So this is correct. Okay. Now I'll try to do some another problems. Okay. Some problem. Here it is says let if P1 P2 are projections on a vector space V over the field F, then P1 plus P2 is again a projection if and only if option A P1 plus P1 is equals to P2, option B P1 plus P2 is equals to 0, option C P1 P2 equals to 0 and P2 P1 is equals to 0, and option D range space of P1 P2 is subspace of the null space of I plus P2. Okay. So let's see. So here it is saying that if and only, that means it should be both sides. So if P1 equals to P2, if P1 is equals to P2, that implies, and for example take P1 is equals to identity, then 2y is not a projection. Why it is not a projection? As 2y square is equals to 4 identity, which is not 2 identity. Okay, so that is the first one. Second one is that P1 plus P2 equals to 0. That is that need, I mean, only in that case, if P1 P2 to projection, then P1 plus P2 equals to 0. It, I mean, if P1 plus P2 equals to 0, then it is projection, that's true. But if P1 plus P2 is projection, and provided P1 and P2 projection, then P1 P2 needs to be 0. That is false. Why this is false? Because, for example, if one takes P1 is equals to projection on the P1 is operator from vector space V to V. V is equals to R2. Let's take V is R2. V from R2 to R2, and it sends P1 sends x comma y is going to x comma 0, and P2 is another projection which is maps from R square to R square, and write P2 x comma y is equals to 0 comma y. Okay, x comma y is going to 0 comma y. Then P1 P2 both are projection, but P1 plus P2 is not equals to 0. Okay, and P1 plus P2 equals to identity, therefore P1 plus P2 is again a projection, okay, therefore option B is correct, incorrect. That means if P1 P2 option B is not correct, so therefore it is not necessary that P1 P2 projection in there and P1 plus P2 will be projection if and only P1 plus P2 equals to 0. That is not correct. Okay, now let's go to the third options. So now we will show that option C and D, if we take these two things simultaneously, then P1 plus P2 will be projections. Now P1 and P2 are projection, then P1 plus P2 will be a projection, then P1 plus P2 is equals to P1 plus P2. Okay. Now P1 plus P2 whole square, that is equals to P1 plus P2 whole into P1 plus P2. And this is equals to P1 square plus P1 P2 plus P2 P1 plus P2, okay, P2, and if P2 square, this is equals to P1 plus P1 P2 P1 P2 plus P2 P1 plus P2, okay, but this should be P1 plus P2, okay, that implies that P1 P2 plus P2 P1 is equals to 0, okay. So now another way, if P1 P2 is equals to 0 and P2 P1 is again 0, that implies that P1 plus P2 whole square is equals to P1 plus P2. That is P1 plus P2 is again a projection, and if P1 P2 is 0, if P1 P2 0, then it is projection, that's true. But if P1 and P2, P1 plus P2 is a projection, then can we show that P1 P2 equals to 0 and P2 P1 equals to 0? We can easily say, can see that P1 P2 plus P2 P1 equals to 0. If P1 P2 not equals to 0, what can happen? Okay, so this will be looked later. Okay, just a minute. I think there is a problem with incomplete. I think there is a problem with this problem. Okay, so now we'll discuss some other problem, and just a minute, I have to find some problem. Okay, this is interesting. Problem here it says, if a diagonalizable operator has only eigenvalue, only has only the characteristics values 0 and 1, It is a projection. It is a projection. Option two option is there, true or false option. So whether it is true or false, this statement is true or false, that we have to check. Okay. So what it is saying is that if a diagonalizable operator has only the characteristics value 0, 1, if a diagonalizable operator has only the characteristics values 0 and 1, then its minimal polynomial is x into x minus 1. Therefore, the operator T must satisfy the equation t square minus t is equals to 0. That implies t square equals to t. That implies t is a projection. So what one can say here is that a projection can have only two eigenvalues, 0 and 1. A projection E on a vector space V can have only two eigenvalues, 0 and 1. These are the only two eigenvalues. Okay. A projection E can have only 0 to 1. If 0 is the eigenvalue, then the projection is 0. If 1 is the eigenvalue, 0 is the only eigenvalue, then projection is 0. If 1 is the only eigenvalue, in that case, projection is the identity operator. If it is a 0 and 1, both are eigenvalues, so in that case, it is a non-trivial projection. Okay. Okay. Now, this is a problem. Okay. Now, problem number 9. Yes, another problem. Let V be a vector space, V be a vector space over a field R, and E be a projection, or I can write idempotent. E be idempotent, that is projection. Idempotent linear operator on V, that is projection. That is a projection. A projection is actually the idempotent. Idempotent means E square equals to E. Then I plus E is invertible. I plus E is invertible. This is true or false. So here, if B is a finite dimensional vector, B is a vector space, any vector space. So E is the projection. Is a projection on R. Then 0 and 1 are only possible eigenvalue. Possible eigenvalues of E. Then 1 and 2 are only possible eigenvalues. Only possible eigenvalues of R E. Therefore, E is therefore only possible eigenvalues of I plus E. Therefore, as 0 is not an eigenvalue of I plus E, so I plus E is invertible. I plus A is invertible. And what is the inverse of I plus A? Okay, so that is something very interesting that I will not discuss here, because that in that case, as 1 and 2 are the eigenvalue, so so I mean, here E is the diagonalizable operator, because E is the diagonalizable operator because it is the characteristic polynomial is x minus 1, that is completely factorized. So therefore E is diagonalizable operator. So if E is diagonalizable operator, so I plus E also be diagonalizable operator. So I plus E is diagonalizable operator, then I plus E inverse, that will also be diagonalizable operator. Okay. So I plus E inverse will be diagonalizable operator. So I plus E inverse will be entirely equivalent to the vector 1 and 2, diagonal element 1 and 2. But I will not write here. Okay. Now we will discuss some other problem. Just a minute, I will discuss one more problem and stop for today. So let's take a matrix A. Let A equals to 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Then what is the characteristic polynomial of this matrix? Minimal polynomial of this matrix. And what is the minimal polynomial of this matrix? What is the minimal polynomial of this matrix? Remember, what are the eigenvalues of this? What are the eigen values of A, and whether it is diagonalizable or not, whether it is diagonalizable or not, and if yes, write A is equals to summation of CIEI with complete description of EI. Of EI. Okay, so here one can look at the matrix A is equals to 0 1 0 1 1 0 1 0 0 1 0 1 1 0 1 0. So here A square is equals to 2 0 2 0 0 2 0 2 2 0 2 0 0 2 0 2. Okay, 0 2. So 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 this is something changed. Okay, now a4 that is equals to will be 0 4 0 4 4 0 0 4 0 0 4 0 4 4 0 4 0. Okay, this is the matrix. Okay, a4. So therefore this is equals to 4 times a. Therefore a satisfies the polynomial x to the power 4 is equals to 4. Therefore, x to the power 4 minus 4 is equals to 0. Now one can write it as x minus root 2, x plus root 2, root 2, and x square plus 2 equals to 0. Therefore, therefore the minimal polynomial of A can be either x minus root 2, it can happen, or x plus root 2, it can happen, or x square plus 2, it can happen, or x minus root 2 into x square plus 2, it can happen, or x plus root 2 x square plus 2, it can happen, or can be x minus root 2 and x plus root 2. But note that neither the operator satisfy any of the polynomial, or it will be so therefore the only possible minimal polynomial, the only possibility, therefore possible minimal possibility the minimal polynomial of A is, therefore possibilities of the minimal polynomials of A, therefore possibilities of minimal polynomial of A is this one, and another is the full polynomial x to the power 4 minus 4. But A satisfies x A satisfies only x to the power 4 minus 4 is equals to 0. Oh, sorry. This is a cube equals to 0. A cube equals to 4a. So this will be x cube equals to 4a. This is x cube minus 4x, right? 4x. So this will change x comma x minus 2 x plus 2. Therefore only possible are x minus 2 x plus 2, or x into x minus 2 x into x plus 2 x minus 2 x plus 2, and x into x minus 2 x plus 2. So one can check easily that only it will satisfy the polynomial, that A satisfies only polynomial equation, satisfies polynomial equation x into x minus 2 x plus 2 equals to 0. Therefore 0 to minus 2 are all are eigenvalues of a minimal polynomial of a is equals to x into x minus 2 x plus 2. Okay, and a is diagonalizable, then a is equals to 2 times e2 minus 2 times e3, where e2 is projection onto the eigenspace. E2 is the projection where E2 is the projection onto the eigenspace of 2, and E3 is the projection onto the eigenspace of minus 2, and E2 is equals to, it will be T times T plus 2 times identity by 2 minus 0, 2 plus 2, that is 1 by 8. Okay, and E3 is equals to 1 by a, sorry, this will not be, this is corresponding to minus 2, so minus 2, this is also 1 by 8. T of 0 2 minus 2, right? So it will be, just a minute. Okay, yeah, got it. So just a minute, I think I have made some mistake little. So 0 x minus 0 x minus 2 x plus 2. So when it is 2, this is 4 into 2, that is 8. When it is minus 2, that is minus 2 into x minus 0, that is minus 2 minus 0, into uh, minus 2 minus 0, and x minus 2 minus 1, minus 2 minus 2 minus 4, so 8. So this is correct, I think. Just a minute, let's verify it once. So 2 times 1 by 80 square, 2 times 1 by 80 square, that is equals to 1 by 40 square. uh, okay, just a minute. Just a minute. 0 2 minus 2 is eigenvalue, there is no problem about this. uh, Corresponding to t, it will be, I think I made some little mistake here, just a minute. E2 is the projection onto the eigenspace of corresponding 2, and E3 is the projection onto the eigenspace corresponding to 3, that's true. Then E1 plus E2 will be identity, right? E1 plus E2 will be identity, that I have to check little bit, just a minute. This is corresponding to, let's write, this is corresponding to, oh no, E1 is equals to, once again, t minus 2i t plus 2i by 0 minus 2 0 minus 2 minus 4. Okay, so this is t square plus 2t minus 2t, so this is t square minus 4 by 4, and this is equals to t square by 8 plus t square by 8, and this is, if we do sum, this is cancel out. Okay, so this is t square by 4. So I think there is minus is needed somewhere else. E2 is equals to T1 E2 corresponding to 2, that will be x plus 2 into corresponding to 2, that is 2 minus 0, and 2 plus 2, that is 1 by 8, and corresponding to minus 2, that is x plus 2 x minus 2, that is minus 2 into minus 2 minus 2, that is also 1 by 8 into this one, and 0, for 0 it is 0 minus 2 0 plus 2, and yeah, that's correct, t minus 2 into t plus 2, so this is 1 by 4 t square minus 4 identity, so if we do sum here, it will be minus identity and t square by 4, so this is t square by, ah, this is correct, this is correct, so this is correct, so this is the expression, so this is the expression. But one thing I just want to know, um, 1 by, this is 1 by 4 t square, plus 1 by 2i, this is 1 by 4 t square, minus plus 1 by 2i, yeah, that's correct, this is correct. So this is the expression. Okay, and also E3 is not here, E1 is the corresponding eigenvalue, E1 is the projection corresponding to the eigenspace, E1 is the projection on the eigenspace of 0, and that is equals to t minus 2i t plus 2i by 1 by 4, I think, that is x 0 minus 2 0 plus 2, this is correct. So we'll stop here, so, and next class is on the next Saturday.